So yesterday you were introduced to the concept of a limit. This is the notation we use, the limit as x approaches a of a function. What you have to do is this. You have to try f of a. You have to put that value that x is approaching into the function for x and see if you can evaluate what it's equal to. If it is defined, if you get a definable result, which means you're not dividing by 0, basically, or I guess we didn't encounter this, but you're not ending up taking the square root of a negative number, maybe. But the bottom line is you are able to actually calculate the value of f of a, then whatever you get is the value of the limit. If f of a is not defined, so you put in the value for x that x is approaching, and you get an undefined expression, then you have to use all of your skills available to you to try to get an equivalent expression that will allow you to substitute that value of x in. And if you can do that, then whatever comes out of the simplified expression is the limit. Be forewarned here, though, that even though you're arranging it so that it accepts x equals a, f of a still doesn't exist. Just because we can get rid of a denominator in the original function and then put x equals a in and get a defined result doesn't mean that a is permissible. You're still not allowed to use it technically. If it's not possible to manipulate the expression enough to accept x equals a, then the limit does not exist. And you're going to kind of following a flowcharty kind of approach here. If you get a defined value for f of a, you can either get a defined value for f of a, or you can get 0 over 0, or you can get non-zero over 0. Those are your only three results. Okay. By the way, the defined value of a includes getting 0 on the top and not 0 on the bottom. 0 over 8 is 0. That's defined. 8 over 0 is not. Sorry about that. Thank you, Annalie. So if f of a is defined, the limit exists and is equal to f of a. The other possibility is when you put in x equals a, you get 0 over 0. And notice that what I say here is the limit probably exists. It doesn't have to, but it probably exists. I don't want to turn this into an algebra lesson from Math 30-1. But if you have a rational expression that ends up giving you 0 over 0 when you put x equals a in, the only way you can get 0 in the denominator if you put x equals a in is if there's a factor of x minus a somewhere in the denominator. It may be buried deep inside of the denominator. It might not be obvious. And the only way you can get 0 in the numerator is to have x minus a in the numerator as well. So if you get 0 over 0, that means that there is a factor that's identical in the top and the bottom. And your job is to cancel those factors. So you have to bring them out in the open somehow by rationalizing or factoring. And then you can cancel them and put in x equals a. We talked about this yesterday. The reason why the word probably is here is that if you have an exponent on that offensive factor in the denominator that's bigger than the exponent on the factor in the numerator, we can cancel an x minus a in the numerator with denominator, but still have x minus a's left in the denominator. And by the way, if that happens, that's going to end up turning into this third situation. Okay. Anyway, the limit probably exists. Your job is to simplify the argument of the limit so that it can be evaluated using x equals a. Once you do put the result in, whatever comes out is the limit. There's a really important point to be made here, though, and it's that even though the limit exists in this middle column, f of a does not exist. Or, I'm going to tweak that a little bit, f of a is not equal to f of x at that point. We're going to talk more about that today with one-sided limits. If this is the result after your preliminary investigation by putting x equals a in, you get a non-zero number like 5 over 0, the limit doesn't exist. It's not possible to get rid of that factor in the denominator. All that being said, does anybody have any questions? And I'm sure there are some. 5a? Okay. So we have 4 plus h quantity cubed minus 64 all over h, and this is a limit of that function as h approaches 0. So the limit as h approaches 0 of 4 plus h quantity squared minus 64 over h. Thank you. Our preliminary kind of exploration is to go ahead and put 0 in. And I don't think you need to show this work, but I'm just going to do it on the side. If I put 0 in for h, well, I get 0 in the denominator. So first of all, if the limit exists, it's going to be one where I have some work to do to tease out that factor to cancel that h on the bottom. Or it could be the limit does not exist. It all hinges on what I get on the top. And when I work out what I get on the top, 4 plus 0 is 4. 4 cubed is 64. 64 minus 64 is 0. So what's happening here is I'm getting 0 over 0, which means I highly suspect the limit exists, but it might not, but it probably exists. And I think I threw out the number yesterday, 99.9 something % of the time. If you get 0 over 0, it exists. So how can I get rid of that h? And again, what this means is that this thing must contain a factor of h on the top. It has to, because there's a 0 over 0. And I don't know, I don't want to get into too much detail here, but how many of you see that since it's h to the 1, the limit will exist? We can't cancel those h's and have extra h's left over in the denominator. So how do we figure that out? Well, one of the things we can do here, Miles, is factor the numerator as a difference of cubes. 64 is 4 cubed. So 4 plus h quantity cubed minus 4 cubed gives me 4 plus h minus 4. And then 4 plus h squared minus 4 times 4 plus h plus 4 times 4 plus h, rather, plus 4 squared. And let me highlight for you exactly what's going on here, because it's hard to see. We have a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. This is our formula for difference of cubes. So what's happening here is I'm equating a with the 4 plus h, b with the 4. It's 4 plus h cubed minus 4 cubed. So I get 4 plus h minus 4. And then I have a squared, which is 4 plus h quantity squared. Then I have the ab, which is the product of my 4 plus h and 4. And then I have my b squared, which is the 4 squared. This is over h. And we're almost done here because this is h. Right, 4 plus h, and then minus 4, all you're left with is h, and that h is now a factor of the numerator and the denominator, so it's gone. And now we can go ahead and put 0 in for h. And when I put 0 in for h, I'm going to get, well, 4 plus 0 is 4. 4 plus 0 is 4. I'm going to get, looks like 16 plus 16 plus 16, which is 48. Is that okay?
Yeah.
Okay, good. All right, Braden, 6g. Let's take a look. So we want to find this limit as x approaches 3 of this expression. One of the things I try to teach my students, and it's very, very helpful, is the idea that when you're simplifying things, that means literally what the word means. Things that are simpler are better. And one of the things that we don't like, let me rewrite this. This is the limit as x approaches 3. X to the negative 2 is 1 over x squared. And what I'm doing is I'm going back to an earlier grade, I guess grade 9 or 10, where if you have a negative exponent, that means you take the reciprocal of the base and you express it to a positive exponent. So x to the negative 2 is 1 over x to the positive 2, minus 3 to the negative 2 is 1 over 3 to the 2. And I could write 9 there, but let's just leave it as 3 squared for now. And then on the bottom, I have x minus 3. So now I'm going to square the 3. Now I'm going to square the 3 and have 1 over x squared minus 1 over 9, and it's over x minus 3. Do those first two little moves make sense to you, Braden?
Yes.
Perfect. So now comes the part that I was talking about. I hate, this is what we call a complex fraction, everybody. I have a fraction. It is a main fraction of a monstrous numerator. The numerator of this fraction is 1 over x squared minus 1 over 9. And it's over a denominator, which is a binomial. It's not so monstrous. But this is called a complex fraction because within the numerator of the fraction, there are many, I call them mini denominators. And I would much rather work with a simple fraction, which does not have fractions within fractions. And I can accomplish that by multiplying the top and the bottom of this by x squared and by 9. And as long as I'm multiplying the top of a fraction by the same things that I'm multiplying the bottom of the fraction by, I'm multiplying by 1, right? That stuff in red, x squared times 9 over x squared times 9 is really just 1. So it's not changing the expression. When I multiply this through, I am going to have to take this x squared times the 9 and multiply it by 1 over x squared and by the negative 1. And what I get is the x squareds canceling and leaving me with 9 in the first term, minus the 9s canceling and leaving me with x squared in the second term. And on the bottom, I have x minus 3 times, I'll just flip this around and write 9x squared. And the point I've tried to make over the past few days is when you're using your tools of rationalizing or factoring, you're doing it with one part of the expression in mind. You're focusing right now, we're focusing on the numerator of this. What I've tried to highlight is if you're focusing on the numerator, don't multiply out the denominator. And by the way, we are trying to get x equals 3 to be accepted into the expression. So it makes sense to leave the x minus 3 in the denominator out in the open. Don't multiply it out. Leave it hanging out there where we can cancel it. Now what I can do is factor the numerator of this. The limit as x approaches 3. 9 minus x squared is a difference of squares, which factors in this case to 3 plus x, 3 minus x. And this is over x minus 3 times 9x squared. This, just to peel it off for a bit, is equal to -1, because if I factor a negative out of this numerator, the positive 3 becomes a -3, the negative x becomes a positive x, and those cancel. And, you know, I've mentioned this before, I think it came up one other time. When you see two things that are negatives of each other, like 3 minus x and x minus 3, just cancel them and throw a negative in somewhere. I don't care where. And now we can go ahead and put 3 in. I'm just going to rewrite this to show everybody what we have left. This is what we have left. So I can now put 3 in for x and get 3 plus 3 times -1 over 9 times 3 squared. And whatever that works out to, I think it's going to be -1 over 9, but maybe somebody could confirm that for me. The bottom, no, it's not. It's going to be -6 over 81, which is -3 over 20, -1/9. Is it? No. Negative. Oh, right. 3 plus 3 is 6, not 9. You're saying -2 over 27? Yeah, that makes more sense. Anyway, Braden, looking at the entire thing, and I know sometimes, particularly over a long distance, that might be a little hard to see on your screen, but was that helpful?
Yes, it was. Thank you.
Oh, you're welcome. Any other questions? All right, so we have one more thing that we would like to look at before we get back to calculus. And this next lesson is, well, first of all, it's found on page 14 of your unit handout. It seems to be kind of out of nowhere. Everything we've done so far has been building on itself. I can always say, okay, to find a limit, we rationalize and we factor. To find the slope of a tangent, we look at basically a limit. It's all been connected. Now we're going to learn about what are called one-sided limits, which, I'll be honest with you, it's an island unto itself right now. Okay? It's not going to be something that becomes very important until someplace in Unit 2. And in Unit 2, when we learn about how to graph functions without a graphing calculator, there's going to be a point where I'll say, that's why we need to know about one-sided limits. Okay? But since we're learning about limits, we're going to talk about one-sided limits here. So we need to understand how one-sided limits relate to what's called an entire limit. And we'll get to that in a bit. We also need to define continuity in a more sophisticated way than you probably think of continuity. We would say that a graph is continuous. We would say that a graph is continuous at some particular value of x. Let's just say x equals a, just using a. We would say that a graph is continuous at x equals a prior to today by saying you can draw the graph past x equals a without lifting your pencil. That's the definition of continuity. Whereas something like the following is not continuous at x equals a, because you cannot draw the graph without lifting your pencil as you pass through a. And if there's an asymptote there, I think it's obvious that it's discontinuous. So the word continuity means what I suspect you think it means. but the definition for continuity is rooted in left and right-handed limits, in one-sided limits. And we're also going to be evaluating one-sided limits. To begin with, we're going to look at what's called a composite function, and this is probably new to you. In Math 20-1, you learn about absolute value functions being broken into what are called piecewise functions. Does that ring a very quiet bell in your head? The idea is you can take, for example, and I don't want to relive that whole absolute value thing from Math 20, but you can take y equals the absolute value of x and change it into y equals x if x is greater than or equal to 0, and y equals negative x if x is less than 0. Because if x is less than 0, you need to multiply that negative value of x by -1 to get the absolute value. But what we basically do is we take a single function and we break it into two pieces. And there's a reason for that. Well, here we're taking a single function and we're defining it as three separate parts. What does this mean? Well, visually speaking, it means that if you look at horizontal measurements of the location on a graph being x, these are x values. This is not necessarily an x-axis, it's just a line. What we're saying is that if you want to calculate y, and x that you're going to use to calculate y is less than or equal to 0, then you have to use the rule x plus 4. So if I were to make a table of values here, and in the table of values, I have -3, then since -3 falls into the subdomain, good afternoon, Jack. Since -3 falls into the subdomain indicated in the red region, I would take -3 plus 4. That's how I would calculate f of x. It would be 1. But if I had an x coordinate of 2, I would not use x plus 4 because 2 is not in that domain. We're on, I think, page 14. Yep. On the other hand, and I'm going with the other side just so I can layer my colors so you can see them better. However, on the other side, if x is greater than or equal to 3, what this statement above is telling us is use 1/3 x. So if I had a table of values and I wanted to generate y coordinates for given x values, and x was 8, I would have to figure out what 1/3 times 8 is to get that value of y. You with me? Okay. On the other hand, if it's between those numbers, and if you look carefully, I didn't want to make these, the purpley lines much thicker than they are because I want you to see how they kind of overlap with the orange and the red. If you look carefully, I have two open dots in purple at 0 and 3, and then they're connected with a solid line. And that indicates that any number that is between 0 and 3 is an x coordinate that you use x minus 2 quantity squared as a rule to find y. Are you clear with what this is telling us? Okay. So the question is, what does the graph look like? Now, I'm going to give you rulers, and if you're in Buck Mountain or Pigeon, you're going to need a straight edge. You don't necessarily need a ruler. A lot of what we're going to be sketching here is not necessarily a straight line. And the exercise here is to teach you about left and right-handed limits and continuity. The exercise does not have a goal that on an exam, I'm going to ask you to sketch these. That's not the goal, okay? So I'm going to show you these graphs bit by bit, and then you're going to graph what I direct you to graph. Okay? So let me open up my graphing program first. There it is. So let's start with the part of the function that goes from -infinity up to 0. Do you agree one part of this function has a domain from -infinity up to 0, and it includes 0? And that function is x plus 4? If I were to look at x plus 4, it's a childlike graph for us to draw. It is, you're not drawing it yet, necessarily. I mean, if you know what we need to draw, you can. But it has a slope of 1. So we go over 1 and up 1, over 1 and up 1, etc. And it has a y-intercept of 4. Except that that is not part of the function we want to draw. Part of the function is in there, but the whole thing isn't part of the function. We only want to draw that from x equals 0 back to infinity. And if I do that, I have a way to enter that. I have a way to tell the graph program to graph only from 0 back to negative infinity. So what this is going to look like is part of that line x plus 4 equals y without the stuff after 0. And you can go ahead and take a minute and draw that line in. And again, if you have a steady hand, I guess you don't really need a ruler. Notice that there's an arrow on the left-hand piece of this composite function, and there's a solid dot on the right-hand piece. I didn't draw attention to it, but I hope you understand there's a solid dot because the inequality statement for that part of the function contains equals. X is less than or equal to 4. I'm going to get rid of that now. And let's look at the middle part of the function. If I were to look at x minus 2 quantity squared, which in Math 30-1 this morning was very challenged in graphing things this morning. I don't know why. X minus 2 quantity squared is a parabola that starts with its vertex at the origin and it's shifted 2 units to the right. But I don't want this to be graphed for all of the real numbers. I want it to be graphed between x equals 0 and, help me out, x equals 3. So I have that one as well. And what that's going to look like is that. I want you to notice something though. This example has been prearranged so that that and this, which you've already drawn, connect. The reason why there's a solid dot where those two meet is not because there's a solid dot on the middle part of the function. The middle part of the function is an empty dot. But as coincidence would have it, I designed the question this way, where that solid dot is on the first part of the function, it happens to fill in that empty spot for the middle part of the function. It's continuous. It's not smooth. It takes a jagged turn, but it's continuous. I'm going to remove these two now, and we're going to look at the graph 1/3 times x, which again is a linear function. It's pretty basic. It's a function with a y-intercept of 0, and it has a slope of 1/3, and it looks like that. But that function only needs to be graphed, and only should be graphed, from x equals 3 to infinity. So what that looks like is that. And as luck would have it, where that open space on the right-hand side of the middle function is, that happens to lock into, it won't always, but it happens to lock into where the other graph starts. And the result is you get this function. And some people say to me, well, where would you have a function like this? There are lots of places where in physical sciences, things change when you get to a certain point. We were dealing with a question just this morning, McKenna and I, and it's a question we did in class where the temperature of the air cools by 1 degree Celsius for every 100 meters you go up. I don't know if you remember that. But it said it was only good for 12 kilometers. So at 12 kilometers for a horizontal variable of height, a new function takes over. And there's lots of cases where nature isn't as simple as saying, oh, it's going to follow this nice pattern forever. It reaches a certain point, and then there's a different law that takes over. For those of you that have taken Physics 30, some of you have taken Physics 30, you know that when you start talking about the laws of governing forces between charged particles, there's Coulomb's law, and then as soon as they get within a certain nuclear distance, the strong nuclear force takes over. Now, we didn't study the formula for the strong nuclear force because it's too wild, but that's an example there. So this is what you should have drawn. Any general questions or specific about this? There's a way to get your calculator to piece this all together, and I might show that to you later. So let's go back now and let's start talking about limits. I'm not going to draw this. You've already drawn it. I'm going to be referring to that graph. What is the limit as x approaches 0 of the function? Well, you'll notice something, and unfortunately, this is the type we usually deal with, the font size. You have to have good eyes. Okay? If I read this stuff on paper with these glasses, I have to take these off and put on my reading glasses. You will notice there's a little negative symbol as a superscript after the 0. And what this is a left hand limit. And you'll notice the limit to the right of that, where it says the limit as x approaches 0, it has a positive for a superscript. This is the right-hand limit. And we read these a certain way. When I read this limit that I'm going to highlight in cyan or blue, I say that's the limit as x approaches 0 from the left. That's what I say, of f of x. Whereas when I read this limit, or think about it in my head, I think this is the limit as x approaches 0 from the right. I don't know if you remember, but yesterday when we did limits, I had that rational expression and we made a table of values that had values of x from the left and the right. Okay, that's what we're talking about. This is called the entire limit. So we need to look at the graph to answer this first question. What is the limit as x approaches 0 from the left? Well, if I go back to the graph, I guess maybe I'll capture this. And I'm talking about approaching 0. Here's x equals 0. So I'm getting closer, I'm on the graph, and I'm getting closer to 0, but I'm to the left of 0. Which means I am here. And then I'm getting closer to 0 and closer to 0 and closer to 0 and closer to 0 and closer to 0. What am I approaching as a function? I'm approaching 4, am I not? Okay. So the left-hand limit is equal to 4. What is the right-hand limit equal to? And this may seem too simplistic. Okay, but there is a point. What is the right-hand limit equal to? Well, now I am here. Now I am here. I'm still approaching 0, but I'm zooming in from the right. Well, not zooming in. I'm getting closer from the right. I'm still getting closer to y equals 4. Which means that the right-hand limit is 4. Okay, so far, so what? The point is I can now talk about the entire limit. If the function is approaching 4 from the left and it's approaching 4 from the right, then the limit is equal to 4. Imagine, if you will, for a second, that the left and right-hand limits are different. Who knew? It could be different. If the left-hand limit and the right-hand limit are different numbers, I can't talk about the entire limit because there's actually 2 limits. What is the limit as x approaches 3 from the left? Well, looking at this graph, as x approaches 3 from the left, I'm on the graph, I'm getting closer to x equals 3, which is here. And as I get closer, remember the idea behind a limit is not what it is at that point, but what do I approach? I approach 1. And if you didn't have any questions with the graphing part of the assignment from yesterday, that should make sense. Does that make sense? Okay. I'm just asking you because you weren't here yesterday. So that's 1. And it wouldn't take a Mensa member to figure out that when you approach from the right, it's also approaching 1. And I know from the expression on some of your faces, you're still going, okay, so what? Since the left and the right hand limits are the same, we can talk about the entire limit having that value of 1. All right. That's all I'm saying here. If the left hand limit, which is this that I'm underlining, this is the left hand limit, is the same as the right hand limit, and believe me, that's not a common abbreviation. That's just me being a little lazy. Then the limit exists and is equal to either of those limits. I want to point something out to you here. It does not necessarily mean the function is continuous. How is that possible? I'm not asking for an answer here. I'm asking for everybody to think about this. How is it possible that when I approach from the left, let's say my nose is at x equals a, that if I approach from the left, y will approach some number, and when I approach from the right, y will approach the same number, but it's not continuous? Do you know, Jack?
If there's a vertical asymptote at that x value?
No. If there's a vertical asymptote, then the function is going to take off like this, and these two values of y, not only do they not approach each other, they don't approach a number. Isaac?
If both functions have opposite domains, so if one of x is less than 0 and x is greater than 0?
I get what you're saying, but that's not what I'm asking. What I'm asking is, what would the graph look like? Forget about the equations of the pieces. What would the graph have to look like if y is approaching the same value from the left and the right, but the function is discontinuous? There's a hole. And we'll get to drawing that in a second. But this is a mistake that people make. They think since the left and the right hand limits are equal, the function has to be continuous there. It doesn't mean that. There's other ways to get discontinuity, by the way. If the left and the right hand limits are not equal, then it's not continuous. But just because they are equal doesn't mean it is continuous. All right. Well, let's talk in more detail about that. What is an example of what a graph would look like if the function was continuous at x equals a? Well, that's what it would look like. I want to point out to you that this point right here exists. F of a exists, and f of a is equal to the limit as x approaches a of the function. This requires a considerable amount of unpacking and explaining. Since if you put x equals a into the function, you get f of a, then based on yesterday's work, the limit is f of a. The limit as x approaches a of f of x is f of a. It's continuous because the left-hand limit is approaching f of a and the right-hand limit is approaching f of a. Any questions with that example? I'll tell you right now, if that statement that I wrote in green is true, that's the definition of continuity. Let's think about that for a second. In order for the limit to exist, the left-hand and right-hand limits have to equal each other. But if they equal f of a, not only do they approach each other, they approach the y-coordinate of the graph, which means the graph has to be continuous through that point. It's going to require a lot of thought. Is there a situation where the limit exists, but it's not continuous. Well, if the limit exists, the left and right hand limits have to be equal to each other. This is just what we were talking about. What you have here is a hole at x equals a. And I'm drawing that awfully big. We know from our discussions in Math 30, and even with a little bit of thought, you non-Math 30 completed students should understand that hole is infinitely small. No matter how close you are to x equals a, you can get closer. But what this looks like, and the nature of the curve doesn't matter, is that. And this is equal to the limit. That's what the limit is. The left hand and the right hand limits are both approaching that value of y. So the limit as x approaches a of f of x exists. However, the limit as x approaches a of f of x is not equal to f of a, because the function doesn't exist at a. And to really throw a monkey into the wrench, so to speak, it could be that it's discontinuous there and f of a does exist. But f of a is this point. Now, why is it that point? Because there's something that happens at that value of x that changes the rules. Just like there's something that happens inside of a nuclear distance that changes the rules for force. And there might be something that happens at that specific value of x in nature that is different. Any questions on that one? What if a function is not continuous and the limit does not exist? Well, if the limit does, think about why the limit doesn't exist. The limit doesn't exist because of this. That is the only reason we can come up with that the limit doesn't exist. That could mean a dozen different things, but at the heart of it, the reason why the limit doesn't exist is the left and right hand limits are not equal. Now, maybe neither one of those limits exist. Maybe one exists and the other doesn't. Maybe they're both there, but they have different results. An example might be this. The left-hand limit would be equal to that number. The right-hand limit, the right-hand limit would be equal to that number. They both exist, but they're different. And the lesson out of this is the following, and it's complicated, logically to think about. Discontinuity doesn't mean the limit doesn't exist. Discontinuous, limit doesn't exist. Discontinuous, limit does exist. Continuity guarantees the limit exists. But just because it's discontinuous doesn't mean the limit doesn't. And that leads us to a very important idea. What's necessary for a function to be continuous at x equals a? Well, what we've said is that in order for you to be able to draw the function smoothly without lifting up your pencil, it has to look like this. The limit must exist. But the limit exists here. and it's not continuous. So what we say here is the limit as x approaches a of the function has to exist, and it has to be equal to something. As soon as I tell you that this limit exists, I'm telling you the left and right hand limits are equal. Okay, so we've covered that. What does this limit have to equal if the function is continuous? Anna? It has to equal f of a. So by saying these two things are equal, you're saying, I think, three things. One, you're saying f of a exists and the limit exists. You're saying that. If you're saying the limit exists, the second thing you're saying is the left and the right hand limits are the same. And the third thing is, if the left and right hand limits are the same and they're equal to f of a, that point they're approaching is a point on the function, so it's continuous. This is the mathematical statement or justification why a function is continuous. And that is what we're going to revisit in Unit 2. But let's do another couple of examples. Consider the following function. This time we have a domain of x being less than or equal to -1. And if x is less than or equal to -1, the function is x plus 3. And you can write this number line graphic down or not. If you do, you want to make sure that when you draw, for example, this one, you have a solid point, and you do that. And then when you draw the other one, you might want to do something like this, just to indicate that it's the other part that's the empty set. Between -1 and 2, and also including 2, when you look carefully at this notation up here, we have a less than or equal to on the 2, but only a less than attached to the 1, -1. That is the function. So anything that is greater than -1 or less than or equal to 2, that's the function. And then afterwards, that's the function. So it's defined everywhere. The question is, do they line up? Do they match up? And I think you can see, well, not see, but I think you'll understand that they will not line up because we already did one where they line up. Let's talk about what happens if they don't. Here is x plus 3. Correct me if I'm wrong, is x plus 3 the part that only exists to the left of -2, -1, and on -1? So that means that, this will be part of the graph, but all this stuff has to go away. And I have that up here. I have it programmed in as a different setting. There it is. I'm not going to remove it because these aren't going to overlap. The middle part of the function is this, except it is only good to the right of -1 and to the left of or equal to 2. So when I adjust what I draw here, I'm going to put an empty dot here, and then I have to put a solid dot here, and everything outside of that little domain is scrapped. Well, what it's going to look like is that. And you can see that they're not holding hands this time. It just didn't match up. The final part of the function is 1/2 x minus 4, which is a linear function. Again, your job, this isn't about you learning how to graph these because you need to do it on an assignment or a quiz. It's about understanding how to read graphs based on limits that are from the left or the right. This one starts immediately to the right of 2. So there's an open dot at the 2. This stuff has to be removed, and we're going to keep that stuff. So when I turn that off, and turn on the third piece, that's what it looks like. Do you see that there are two discontinuities here? That means that the limit as x approaches either of those values of x will not exist because the left and the right hand limits are different. Oh, you know, I misspoke there. I really did. Just because it's continuous doesn't mean the limit doesn't exist. The limits will not exist because the left and right hand limits are different. So looking at this now, let me capture it so we can load it into our example. What we are asked to do I hope I have those here. Well, for some reason, I don't know why, I've lost. There they are. Are these them? Okay. Oh, I was on a different page when I grabbed it. So, we want to know the limit as x approaches -1 from the left. Well, here's -1. Here's our point on the function to the left of -1. As we get closer to -1, y will approach 2. However, when we're on the right-hand side, as we get closer to -1, y will approach 4. So the left-hand limit is 2, the right-hand limit is 4. There's no limit. You cannot say, well, what's the limit as x approaches -1? Because that's not a mathematical symbol, right? The limit doesn't exist because it's ambiguous. You can't say a number. By the way, you don't average these. I had a student one year ask me, well, can't you just average them? Yeah, that doesn't work in math. That's not a good idea. So that doesn't exist. What about as we approach 2 from the left? Well, as you approach 2 from the left, y will approach 1. It's getting closer to this value of y. As you approach 2 from the right, y is approaching -3. So the left-hand limit is 1, the right-hand limit is -3. I just lost my train of thought in going from one page to the other. Do those line up with the graphs you've drawn? Okay. And again, nada. There's nothing here. You can write doesn't exist. But I think you get the point. All right. One final example. What is it you do if you're asked to evaluate a left or right-handed limit and you don't have a graph? You have an actual equation. There is no algebraic way to do this. When you talk about the limit as x approaches 1 from the right of a function, you're talking about x being a number to the right of 1 that's getting closer to 1. And the only way you can find out what this is, well, not the only way, the best way I think right now for you to think of it is ask yourself what that thing approaches when you put in a number like 1.000001. And what I would say to you is when you take 1.000001 and square it, it becomes slightly bigger than 1.0001. Slightly. And if you then subtract from that slightly bigger number, 1.0001, you're going to be left with a little tiny, tiny thing. So in theory, thinking about this, this should be 0. If we were to do that, and I didn't ignore the square root, I just didn't talk about it. When you take the square root of an infinitely small number, you should get an infinitely small number. So 1.00001 We want to square that and subtract 1.00001. We get this little tiny number, 1.0 something times 10 to the negative 5, which means 0.00001, 0.00001, probably repeats. I take the square root of that, and it's pretty tiny. If you were to continue to put in a smaller and smaller and smaller value of x, I want to be careful of that, getting closer to 1 but not passing 1, what you would discover is it's 0. What about the left-hand limit? What you would discover is it's approaching 0. Well, with the left-hand limit, here's what we want to do. And I would ask everybody to think about what it is you're going to get if you start putting in numbers for x like that. Now, those of you that have not taken Math 30-1 yet are at a disadvantage. Because something you learn and we talk about in 30-1, which comes as a surprise to many students, is when you square a number, it doesn't always get bigger. If you square a number that's less than 1, it gets smaller. And you can try this. Take 0.999 and square it, and you're going to get a number less than 0.999. And that means when you subtract 0.999 squared minus 0.999, you get a negative number. And you can't take the square root of a negative. So this limit does not exist. That means this limit does not exist. Why does this limit not exist? Because the left and right hand limits are two different things. 0 is not the same as nothing. But I shouldn't. You can see what the assignment is, page 27, 1 to 9. To find a left or right-handed limit, investigate the value of the function very close to a, but on the left or the right. And if you have an equation, you can use an equation. If you have a graph, you can use a graph.